I'd like to talk today about something that's become like an eternal triangle between welfare, disease, and behaviour. I started out being interested in behaviour, then I've got interested in how behaviour could be used to define and recognise welfare. Obviously, disease, or rather the absence of it, is an important part of welfare. Then I got interested in the other way around, the effect that disease could perhaps welfare could perhaps have on disease, and good welfare might actually help with disease resistance. And then how disease affected behaviour. So I come round in a kind of circle, triangle. And so I hope that there'll be something for everybody today. What I'd like to do is really say a little bit about the background of chickens and welfare behaviour, then how it's possible to use behaviour for assessing welfare and disease. Say a little bit about the relationship of groups and individuals, because I think it's important to remember that welfare is an individual issue. And then finally, I'll say something about our attempts to improve chicken welfare in practice. I'm sure most people are aware that broilers, meat chickens, are not kept in cages. They're kept in very large sheds, a bit like aircraft hangars, in very large groups. 30,000 is actually relatively small. They can be 40, 50, even 70,000. And sometimes, but not always, there are windows down the sides to let in daylight. Sometimes they're kept completely in artificial light. And they have this very characteristic stocky body shape with a lot of on the breast meat, because that's what people want. And they grow extremely fast. They will reach their slaughter weight in less than 5 weeks. So a chick will go from fluffy little chick to chicken tikka masala in less than 35 days. And this astonishingly fast growth rate is partly a function of their being fed rocket fuel as diet, and partly because of many years of selective breeding to grow fast in the juvenile stage. And this very rapid growth rate has had a number of welfare issues, basically that not all parts of the body keep up quite as well. So they have often have they have problems with their heart, and they also have problems with their skeletal system, which often makes them lame. So a combination of this kind of way they're kept and the very fast growth rate has meant that a lot of people are increasingly concerned about their welfare. But surprisingly, there are not really very good ways of assessing the welfare. Most of them are post-mortem. They're done after the birds have been killed. So there's no chance of actually intervening or improving the welfare while they are still alive. And you can see they're pretty crude. I mean, percentage mortality as a measure of welfare is a pretty crude measure. Pododermatitis refers to these blisters, ulcers that occur on the feet that get infected, and then the toes swell up. And hockburn are these burn marks on the legs caused by sitting on usually on wet litter. So these quite crude measures after death. While the birds are alive, sometimes, but not always, people go in and what is known as gate score them. That is, they watch a few individuals walking and give them a score of 0 means good and 5 means dreadful. So, but that doesn't happen all the time. And even if it does, it is only a snapshot and not a wonderful way of keeping disease out of chicken houses if you've got the same team growing around. So really, basically, for most of their life, there's no real assessment of welfare. And what we've been trying to do is to develop a method of continuously monitoring welfare so that we can fill in that gap and allow interventions while the birds are still alive, while you can still do something about it. Now, with a group of a very large group of 30,000, the idea of tagging is very difficult because you have to put the tags on, then you have to get them off again. And even individual tracking from video would be difficult. It would be possible, but it's difficult with thousands of identical white birds. So we opted for a rather different system, a much simpler system, which was to analyze the movements of whole flocks using optical flow, which I'll explain in a moment. And this is completely non-invasive. We simply have a camera in the house and a small computer that analyzes the video immediately on the spot. And because it's so computationally simple, it can be done in real time. It can deliver a verdict every minute, every 15 minutes, whenever we want. And it can run throughout life without running into storage problems, because you're not storing videos, you're only storing the numbers that come out of the analysis. And it's obviously very secure because no videos leave the farm and only numbers leave the farm. So we've opted for that system. And basically, it's a very simple method of analyzing movement. So if you see successive frames of video, each frame is divided into 8 by 8 pixels. And if there is no movement between frames, all the white squares will remain white and all the black squares will remain black. If there's movement, then some of the white squares will become dark and some of the darker squares will become light. And that rate of change of image brightness is what's known as the optical flow. So it's a very crude, simple system for doing that. And you can see it doesn't do anything fancy. It doesn't analyze his face or his hand. It just gets very, very excited if it sees movement in one place, but not in something else. So it's not tracking individuals. It is looking at whole flock movements. And the kind of output that we get is this shows you the mean output. I literally picked this at random. It was what happened to be sitting around my desk from the last one of the last lot of flocks we were looking at. And you can see at the beginning there's a bit of a mess, and then it settles down into this beautiful night day pattern. And as I say, we initially calculate the results every 4 seconds and every minute. What I'm going to say from now on is always mean for a whole day. So it's mean optical flow, mean optical flow, daily mean optical flow. And the reason we take whole days is we found that it just gives cleaner correlations because it doesn't get distracted by things happening in the house, people walking through it, or electricians or thunderstorms. So we just get cleaner results if we do that. But obviously we've got that data, and we have also looked in finer detail on a finer timescale. And in addition to the mean, we also look at variance, skew, and kurtosis. And variance isn't particularly informative, but skew and kurtosis are. I apologize if I'm just telling you something you already know, but my experience is that even statisticians get a bit bemused by kurtosis. The skew obviously is, if the orange here is a normal distribution, the skew tells you the extent to which a normally symmetrical normal distribution is displaced to the left or to the right. And a positive skew means you've got the mode to the left with a tail on the right. So if you imagine a distribution, a movement distribution from this optical flow with fast movement on the right and slower movement on the left, that's the skew. The kurtosis, again, the orange is the a normal distribution. A kurtosis refers to the extent to which you've got data in the extremes or tails of the distribution. As you know, that in a normal distribution, most of the observations would be expected to be within 3 standard deviations of the mean, either side of the mean. If you've got a lot of observations outside that, you've got what is known as fat tails and a kurtosis, a positive kurtosis. Obviously you get a positive kurtosis on either tail, but the sign of the skew will tell you which tail you're actually dealing with. And this is, again, just, I could take any examples, just a number of recent flocks we happen to be looking at. Typically, you get a positive skew and a pretty high positive kurtosis. And the interpretation of that is that this positive skew shows you've got the mode to the left, a lot of movement below average, and the positive kurtosis shows you that you've got some rare activity in the tail of the distribution. And this corresponds very well to direct observations on broiler chickens, which show the majority at any one time, between 80 and 90% often, they're just sitting and lying, not doing very much. And then you've got a small minority actively walking. So both direct observation and the optical flow pattern shows the same thing. So that's what it does. And so the next question, what can it actually do? Well, one of our first studies involved making correlations between the optical flow variables and these indications of poor welfare that I mentioned before. So obviously these are indications of poor welfare, so the higher the incidence of those, the worse the welfare of the flock. And what you'll notice is that the mean is negatively correlated with these things. So the higher the incidence of these poor welfare indicators, the lower the mean optical flow, the lower the mean amount of movement in a flock, which kind of makes sense. But what's so interesting is this consistent high skew and kurtosis of the optical flow. And what that means is that the higher the level of these poor welfare indicators, the more positive the skew, i.e. the further to the left the distribution goes, and the higher the level of the kurtosis as well. So you've got more birds sitting down around, and you've got not more birds walking extremely fast, but fast movement has become rare. So you've got a shift to the left of the skew, and then you've got this tail becoming where fast movement has become even more unusual. And obviously in a healthy flock, you would expect everybody to be walking reasonably fast. In an unhealthy flock, healthy walking becomes very unusual, and that's a sign that there's something pretty badly wrong with that flock. And one kind of analogy you can think of is that skew and kurtosis are both measures of variability in movement. So if you had a race run by high quality women athletes, the mean movement would be high, and you wouldn't have tails in the distribution because they'd all come in pretty much at the same time. But if you had a race with men and women and amateurs and professionals and people with silly costumes on, the mean would be lower, but equally you'd have more tails, a fast tail and a small tail, and you probably have a shift in the mode as well. So they're incredibly useful things for telling you, if not about individuals, at least about proportions of different individuals behaving in different ways. Now, the thing I showed you before was just simply taking a single day, which happened to be day 30, and then correlating it with these welfare outcomes. What we then did was to say, well, we've got information about the whole lifetime of the flock. We can look at all the days, and we can each day correlate with these end welfare outcomes. This is just for one of them, for Hockburn, those marks on the legs. And so each day we would say, can we correlate the optical flow variables? All four of them went into the model with a final outcome of Hockburn measured after the flock had been killed. And so each day we say, now can we predict? And then the next day we'd say, given that we know the day before, now we can predict better. And the extraordinary thing that happened for this was that we got significant correlations by the time the birds were only 3 days old, though by that time there was no sign of Hockburn or dermatitis. There's no sign of it at all, but it was kind of predictive of something that was not going to be measured for another month. So even before the signs of poor Hockburn or leg damage occurred, the cameras were picking up something odd about the birds, about the flock. And we've recently, this is the paper I circulated, we've recently repeated those experiments on a new set of UK farms and on Swiss farms. And the significance of Switzerland is that they do things differently there. They tend to have maybe one house per farm, whereas in the UK it tends to be 6, 7, 8, 9, 10. They have more enrichments. The birds have access to little verandas where they can go outside. So it's quite a different setup. And yet you can see we've got very similar results. We can begin to predict the mortality at about 5 days and the hot burn at sort of ridiculously early ages of 2 or 3 days. So we feel that, I mean, replication obviously was quite important. And I think we now feel, having looked at over 300 commercial flocks, we feel reasonably comfortable with saying poor welfare flocks are slower and more variable. That is, they've got a lower mean, higher skew and kurtosis, whereas higher welfare flocks are faster and more uniform, higher mean, lower skew and kurtosis. And that seems to be quite a robust finding. So we then had asked, well, okay, these cameras, the optical flow approach can pick up welfare outcomes, but what about actual disease and infection? And at this point, I joined forces with Martin Maiden and Fran Collis and Adrian Smith, and we put together a grant proposal on the relationship between disease and this behavior as measured through the optical flow. And we almost didn't put in Campylobacter. We put in Amelia and Clostridium, nearly didn't put in Campylobacter because it was thought that it's zoonotic. That is, that the chickens are carriers, but they're not affected by it. And if they're not affected by it, well, it's not going to affect their behavior. So we're not going to pick up anything. But at the last minute, almost, we decided we would put in Campylobacter because it's such a problem for, at least for European poultry producers. And we thought it might sort of help with the grant application. So we designed this experiment in which we worked with 2 different poultry producers in different parts of the country, one up in Hereford and the other one down in Devon. And we had our optical flow data from day 0 when the birds arrived right the way through life. And we collected fecal samples with boot socks at 21, 28 and 35 days. If you're not familiar with boot socks, they're socks you put on the outside of your boot, and then you tramp around the chicken house and the socks get mucky, and that muck is effectively a sample. Obviously it's a bit hit and miss. So we also collected fecal samples at 28 days. And as I say, we were not expecting any particular result from this. We didn't think it would be affecting the behavior of the birds. So when the results for the first company came through, we were all really quite astonished that we did get a separation of flocks, of the 2 kinds of flocks. So in the green are flocks that never, right the way through their life, including right at the end, never had Campylobacter in their feces that could be detected by culture. I should say it was done by culture at this stage. Whereas the blue flocks are flocks that at one of those days, 21 or 28 or 35, had fecal samples that delivered a positive result through culture. And the data are plotted by taking a farm median and then looking at the deviation of each group from that median. And you can see that the Campylobacter-free group had a higher mean than the median, the farm median, and a lower kurtosis, whereas the blue group, the positive group, had the lower mean and the higher kurtosis. So we got exactly the same pattern and also the same early separation of the 2 groups. So we were obviously on tenterhooks to know what was going to happen when we took the results from the second company, and we found an even stronger signal there, an even greater and more obvious separation of the two groups. So it was a surprise to everyone. And at that time, we thought, well, there's two explanations, and we're not quite sure which way the causal arrow goes. Either that there are some chicks that very early on are already infected. It's just that it's not detectable by the culture method. And so that explains it. I mean, we're looking at the infection just occurs much earlier than people had thought. Or that they're not infected, none of them are, but the fact that they've got a difference in behavior indicates that perhaps some of them are more susceptible to later infection. So we're not looking at infected chicks, we're looking at potentially infected chicks. So obviously it was really important that we looked at the fecal samples of much younger birds, of much younger than 21 days. And Fran talked last term about her really rather amazing result that showed that if you look at the fecal samples from very young birds, they've all got it, but in very tiny quantities that aren't detectable by culture, but can be detected by deep sequencing. So in a way that it becomes even less clear what's going on, and we don't really quite know what's going on, and that is still something that we're still looking at. I think we're all, that group of us are quite pleased, but the way the behavior and the disease kind of spark off each other and show things that either one of them alone couldn't show. So quite clearly, this behavior that we can pick up and we can automate is not only assessing welfare and infection, it's actually predicting it. It's actually enabling us to say at a very early stage what is going to happen to those flocks. I just say briefly about how the optical flow, which is a group level measure of welfare, and all these percentages of this, that, and that are group levels. How does it actually relate to the welfare of individual birds? Because, as I said, the welfare is an individual matter. I mean, never forget about the individual in all of this. And this is work done by our colleagues Sabina Gebhardt and Marian Stratman in Bern. I've already mentioned that we were working on Swiss flocks, so there were cameras collecting optical flow data in the Swiss flocks, and what Sabina and Marian did was to go round to each of these flocks while they were still alive, extract 16 birds from each group and give them individual behavior tests. They did this when the birds were 3 weeks old. And they gave them 3 tests, all designed to test their mobility activity in different ways. They gave them a runway test, which is quite simple. You just put the bird down there and it walks down to meet its friends, and you measure the amount of time they took to go down there. So obviously active birds move quickly, so expecting a small time to be associated with activity. And then in the second runway test, they put some bricks, some obstacles just there, so that bird had to jump over. And they also gave each one a so-called latency to lie test, which has been validated quite extensively, not by us, but by people in Bristol, in which it's been found that birds with weak legs tend to sit down quickly, whereas birds with good legs keep standing. And in order to standardize the test, the birds are put into a shallow dish of water. The ones that have good legs keep standing for as long as the test goes on. The ones that have weaker legs can't help sitting down, so they sit down in the water. So you measure how long the bird remains standing. And obviously in a water test, activity or good mobility goes with a long time. So I just mentioned that because the different ways of measuring activity give rise to different predictions of what you'd expect the relationship to be with the flock from which they came. So what we did was to correlate the behavior in these 3 tests with the optical flow values of the flocks from which those birds came. And again, I mean, quite unexpectedly, we found that there was a good correlation, despite the fact that we're only taking 16 birds out of flocks of 30,000. And basically what this shows is that the birds that took a long time in the runway test came from flocks with the highest skew and kurtosis, and the birds that came that stood up the longest time in the water test came from the flocks with the highest mean. So it takes a little bit of time to get your head around it, but I can assure you it is the right way round. The least active birds, the slowest in the runway test and the fastest in the water test, come from flocks with the lowest mean and the highest skew and kurtosis. So it's actually quite interesting that there does seem to be this quite close correlation between the group level measure and the individual tests. And then just finally, I'll say a little bit about how we've set about trying to get this system widely adopted, and how we're trying to get it widely used. And I mentioned the fact that we've now got data on over 300 flocks. And in talking to farmers, they want to know very early on, as early as possible, which of their flocks are doing well, which flocks are problematic and are going to need special attention. And if possible, they would like to know what the problem is. So we devised a traffic light system, green to show good welfare, red to show poor welfare, yellow in between, so that a farmer could easily see how a flock was doing in relation to other flocks. And we did this by taking what we call reference flocks. So we, having got quite a lot of data on a lot of flocks, we know what the optical flow patterns of flocks which ended up with good welfare, i.e. Low levels of hop burn, low levels of pododamatosis, low levels of mortality. We know what their optical flow pattern looks like. We also know what the optical flow patterns of poor welfare flocks are. So effectively what we do is we ask, does a given flock look more like a good welfare flock or a poor welfare flock? And we plotted this as on a graph, so make it as easy as possible for the farmer to see what was going on, where the green area is where we expect the optical flow patterns of the high welfare flocks to be, and the red area is where we expect the optical flow patterns of the poorer welfare flocks to be. And again, this is plotted as a deviation from the median. Now, so if you look on the right-hand side here, this is a flock that ended up with 0% hock burn, a high welfare flock. And you can see that right from the beginning, it looked like other high welfare flocks. Whereas this flock, which ended up with a truly awful score of 70% hock burn, right from the beginning, it was very different and looked much more like the poor welfare flocks. And again, notice that this happens right from the beginning. The difference is apparent right from the beginning. And so what the farmer actually sees on his smartphone or his screen is a daily update of a flock in relation to what is expected to be good or poor welfare. So it's a daily update on what he's what the flock is like, what the flock welfare is like. So we've obviously been thinking about the future of this, and could it be widely used? Could it be taken up? And thinking about the future, as you probably know, agriculture is undergoing some major revolutions at the moment in terms of adopting technology. And we realized that the future of that is not to set up our system, which we call optic flock, on its own, but to combine it with all sorts of other things that are already being collected. A lot of farmers, particularly in the States and on the continent, already have dashboards which are collecting data on humidity, temperature, body weight, food and water consumption. And we didn't want to have a situation where the temperature is in one place and the water consumption gauge is in another place and the optic flock is in a different place. We wanted it all to be together. So the farmer would have everything about a flock all together. And so our system would just plug into an existing dashboard and be an extra, a welfare indicator on top of everything else. So we've recently signed a development license with a big company that already has dashboards in farms, and as I speak, they are working to make it integrative with the whole lot. So everything about a flock appears in one place, and a farmer can then make an informed decision about all of the things, all of the information that he has. And again, it must be the case that agriculture will be making so much more use of big data sets. They've been collecting data for years, but never making much use of it. But the future must be that we can specify the risk of disease or the situations for good welfare, not in terms of, oh, well, I think it could be this, or in our experience it's that, but based on data from databases from thousands and thousands of flocks. So it really will be properly data-based and data-driven in the future. So we want optic flock to be in there, giving data, part of that picture. So that's another reason for integrating it with other sorts of data. We've designed it so it can be standalone. You can just use it, or it can be integrated with other data. So the triangle. Where have we got to with the triangle? First of all, I think we have shown that behavior can predict welfare and disease even before clinical signs are apparent. So it's going to potentially very useful for predicting as well as just assessing welfare. That the optical flow patterns arising from flock movements do provide a way of automating and the whole assessment and give a continuous real-time welfare and disease monitoring. They also give early warning of health and welfare problems, which can allow early intervention, and that we feel that this should be part of the future. We hope it will be future of agriculture, because greater health and welfare can also have other benefits, such as reduced waste and targeted and therefore reduced medication, perhaps preventing producers from succumbing to the temptation of using a medication as a prophylactic and only using it when it's really necessary, because they will have the early warning of which flocks are really in danger. So I think that's what I'm going to say, and just say thank you to everybody who's contributed to this project, and I'd be very happy to answer any questions.